All right, you guys, we've got our last video of the chapter, second to last chapter of the year. We're getting very close to the end here. I have a couple of vocab words for you to start copying down in reference to this graph right here. So this is a crazy looking piecewise graph with a bunch of like weird stuff happening. And I want to first of all define these different types of discontinuities. And so places where the graph is not continuous. The very first spot is right here at x equals -1. The reason for that is because if I was tracing this graph with my pencil and I get to this open circle right here, I would have to lift up my pencil and then come down here to continue with the graph. That's called a jump discontinuity. And the clue there, like I said, is that you have to pick up your pencil if you're tracing it. It's a little bit different from what we call an infinite discontinuity, and that is when that happens at x equals 0 here. Here is the y-axis, so this is x equals 0, and that's because from the left-hand side we're going towards positive infinity, that's why it's called an infinite discontinuity, and from the right-hand side we're going towards negative infinity. And so that's an infinite discontinuity because you're using the infinities. The third type of discontinuity happens at x equals 2, and that happens to be right here, and that's because it approaches the same value from the left and from the right, but there's a hole right here, and it's a point discontinuity where just a single point is discontinuous there. So the open circle is here and the closed circle is up there. That is called a point discontinuity. So these are the three different types of discontinuities that we have. Okay, for number 2, state the intervals where g of x is continuous. And so this is kind of similar to when you were in Algebra 2 last year and you had to do intervals where, for the domain or the range. This is a little bit different. It's not like the domain because it's a different type of like open circle, closed circle, bracket, parenthesis situation. So that's the difference. But these are all x values here. That's how you define intervals, is you always talk about the x values. Okay, so the first part is that it is continuous starting right here, which happens to be -3.5. These are going by half steps. So the x value of -3.5, and it's continuous, 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 continuous until here. This is the x value of -1, and that's where we have our jump discontinuity. And so that's why I'm putting a parenthesis on -1, is because it's not continuous at -1. That was the first thing up here that I defined as not being continuous at that x value. Okay, so then I jump and I come down here and I'm continuous, continuous, continuous until I get to 0, and that's the next place where it's not continuous. And again, those are parentheses there because it's not continuous at 0. That was my infinite discontinuity here. And so again, at 0, now I'm continuous, 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 continuous until I get to 2. That's the last spot where I'm not continuous, and that was our point discontinuity. And so again, 2 with a parenthesis because it's not continuous there, up until 3. And you can just bracket 3 because we don't know if it's continuous or not there. So the endpoints here get brackets, and then all these other x values where it's not continuous have parentheses on them. So kind of like domain, but don't think about open circle, closed circle the way domain was. Think about it in terms of, is it continuous there or not? If it's not continuous, it gets a parenthesis. Okay, so big concept of the day. Something for you to copy down before we do just a couple brief examples is how do you prove that a certain function is continuous? And so there are 3 steps that you have to show, and this is very important that you get these copied down because I literally, in my answer keys and stuff, number them 1, 2, 3, and then that's how I do the proofs. Okay, so we have to prove that the limit of f of x exists, meaning it approaches the same value from the left and the right. So remember how if something is dne, that's because it approaches a different number from the left and the right. This is how you prove a function not continuous. So like this is the opposite of this. Okay, the second thing is to prove f of c is defined. That means when you plug in this little c number to the equation, you're actually able to do it. Remember how sometimes you plug in that number that the limit that the x approaches, and it gives you something like undefined, like gives you something like a denominator equals 0. You have to make sure that that doesn't happen. So plug in the number for the x value that you're approaching for the limit and make sure that it actually is defined. Or if it's not continuous, maybe it's undefined, like some of those examples that we've done. Okay, and so then the last thing is you have to show that the limit as x approaches c of f of x equals the number when you plug it in. So basically you have to prove that this equals this. And that's the third thing. If they're not equal, that means it is not continuous. So I know that this is probably a little bit confusing, and this is like a bunch of symbols and stuff that we're still not totally familiar with, but let's look at a couple different examples and see how it works, okay? So we're gonna move down. Next page, explain why g of x is not continuous at x equals 1. And so not continuous, that's kind of choose one of these options up here. All you have to do is show that one of the above rules doesn't pass, and that means that it's not continuous. So let's look at x equals -1 on this graph. Here's -1. Can you first of all define what type of discontinuity this is? From way up here. What does it look like? X equals -1. Oh, it's the same graph. I did that on purpose. This is our jump discontinuity. So what I want to look at here is the limit. Let me zoom in a little bit. Limit as x approaches -1 from the left of g of x. What is the limit as x approaches -1 from the left? So as we're getting closer to -1 from the left, the y value we're approaching here is +1, okay? What about as I approach from the right? Limit as x approaches -1 from the right of g of x. So let's look at the graph and look from the right. So from the right, we're going closer and closer and closer to, oh, we land at 0, okay? Because these are not equal, that means that the limit as x approaches -1 of g of x does not exist. And so that happened to be, you guys, the very first thing up here. The limit does not exist, and that's because we're approaching different y values from the left and the right. And we've already done that, but that was the very first thing that I tried to prove to see if it was continuous. So therefore, since they approach different numbers, the limit does not exist, therefore it's not continuous. So let's look at x equals 2. So x equals 2 is right here. And so let's see what type of a discontinuity this is. This happens to be a point of discontinuity. There's a hole there. And so let's look at the limit as x approaches 2 from the left of g of x. So as I'm approaching 2 from the left, let's see, getting closer and closer and closer to the y value of 1, okay? I know there's a hole there, but I'm still getting really close to 1. Let's look at the limit as x approaches 2 from the right of g of x. So as I'm approaching from the right, I'm getting really, really, really close to also 1. Okay, so the limit exists, and the limit is 1. So the limit as x approaches 2 from either side, g of x, equals 1. Okay, so it passes test number 1. Is it defined at 2? Okay, so when I plug in 2, even though I have a hole here, there's a dot right there, so I get 1.5. So it is defined. It's not undefined. There's not an asymptote there, so it passes test number 2. Let's try test number 3. Is the limit, I'll do this in a different color, is the limit as x approaches 2 of g of x equal to g of 2? Okay, so remember the limit I got was 1. But what happens when you plug in 2? When you plug in 2, or if you look at the 2x value, that's an open circle. The closed circle is right here. That's 1.5. The dot at 2 is open at 1, but closed at 1.5. That means this side is 1.5. Those are not equal, therefore it fails test number 3. And that is the reason why it is discontinuous, or not continuous is the wording here in the question, at x equals 2. So I went through all 3 of my tests, and it happened to be the third one that didn't pass. So even though the limit exists, you guys, from both sides, it approaches 1, but when you look at the x value of 2, the answer is not 1, it's actually 1.5. That's what the left side here doesn't equal the right side. Okay, why is it continuous at x equals 2? So that's not why is it not continuous, it's asking us why is it continuous. So I'm going to go through those 3 steps 1, 2, and 3 from the page before. So step 1 says the limit as x approaches negative 2 of g of x is, let's look at what the limit is. Excuse me, from negative 2, it looks like I don't have any funny business happening here. As I approach from the left, I get close to 0. As I approach from the right, I get close to 0. They both meet at 0, therefore the limit is 0. So you totally could have split it up into left-hand side and right-hand side and done that separately. But just to save like space on my paper, I guess, I just did it all at once. I looked at both sides. They both go to 0, therefore the limit is 0. Step 2 is it defined at x equals 2? And so at x equals 2, I get 0. So g of 2, or negative 2, excuse me, equals 0. So that means it's defined. I don't have like an asymptote there. If I was plugging into an equation that doesn't give me 0 in the denominator, I don't have the equation for this one, but if you did, that's what you would do, is you would try and plug in negative 2 and make sure it is defined. So it is. So it passed test number 1 and test number 2. Let's look at test number 3. That says that the limit as x approaches negative 2 of g of x is supposed to equal g of negative 2. And so this, the limit was 0. I did that up here. And when I plug in negative 2, I get 0. It passes all 3 tests. And so for that reason, g of x is continuous at x equals negative 2. Okay, so one more time really briefly, because this is the last problem I'm going to look at. We'll save the rest of it to do in class. But the first thing you have to do is make sure the limit is defined. Do they approach the same number from the left and from the right? They do. They both approach 0. Cool. Second thing is, at that x value that you're testing, you have to make sure that the function is defined. Okay, if I would have plugged in 0 here, see how it doesn't actually touch 0 ever? That would be an example of not passing. That would be undefined. There's an asymptote there. But at negative 2, there's no funny business happening. At negative 2, I have just a regular old point there, negative 2 comma 0. That means g of negative 2 is 0. It is defined. There is a point on the graph at negative 2. It happens to be at a y value of 0. The third thing is to make sure that like the answer for number 1 equals the answer for number 2. And so that was 0 equals 0. The reason, or an example of that not working is this one up here. Remember how it approached 1 from both sides, but there was actually a dot at 1.5 and those numbers were not equal? That failed test number 3. And this one it passed test number 3 because both of number 1 and number 2 were 0. Okay, so I will do a couple more examples in class, and then we've got lots of time to practice before the test, which is in just a couple days. Bring your questions to class. Thank you guys for watching. Last video of the chapter. Congratulations, 1 chapter left. I'll see you tomorrow. Have a good night.